Got it recording. Sorry, awful way to do class, I know, but we'll try it out.
Minecraft. Same.
Yeah.
Okay. Let's see. So let's really quick review last thing that we talked about. What was last week's lecture all about?
Non-random.
Random variables, worst named things on planet Earth. What is a random variable?
It's a function that maps everything in your sample space to a real number.
Yeah, maybe we should start with what's the mathematical model we've been using? We've been using something called the sample space. And so our sample space, that's been this thing right here, this S and this P, where S here is, no, the whole thing together is your sample space. What is S? S is just a set, but it's a set of what?
Your outcomes.
The set of all possible outcomes. So S is everything that could possibly happen, and then the P is your probability function.
Yeah.
So that's S and P. What are the restrictions on our probability function?
Can't be negative, and everything in it has to add up to 1.
Can't be negative, no such thing as negative probability, and all your probabilities have to add up to 1. Make sense? Coming back to you, zoning in a little bit.
Trying.
All right, it's good to try. Okay, so then we had the notion of a random variable. In particular, we were going to be talking about now real random variables. So that's this X right here.
Yeah.
What is a random variable? It's just a function whose domain is S, your set of all outcomes. It maps every outcome to something. A real random variable maps to the real numbers. That's why it's called a real random variable. So it takes everything in S and maps it to some real number. So for example, your probability function, you can think of as a real random variable. It's a function from S to R. So any function that maps everything in S to some real number, we call a real random variable. And then when you have a real random variable, you can use that to then calculate what we call expected value. It only makes sense to calculate the expected value of a real random variable. A lot of terminology. Coming back to you. Now the scary part. What was the definition of expected value? So that's right here. The expected value of X, what is that equal to? It's equal to the sum for every little s and big S of X of S. Remember, X maps S to some real number. Times P of S. Remember, P maps S to some real number. P of S is just the probability of S occurring. X of S is just whatever X maps S to.
What's the weird symbol again?
Oh, the sigma here?
Yeah.
That's your sum sign. It means you're doing a sum for all those things.
Right.
So we read this, just reading it. This is a sum for all little s and big S of X of S times P of S. That's just reading it out. So you plug in, for every little s and big S, you plug it into these two things, which will give you some number, and then you add it to what you get when you plug in the next thing in little s. And you keep taking things out, or take the next thing out of big S. So grab something out of big S, plug it in, that'll give you a number, add it to when you plug in the next thing from S. Let's do a concrete example to remind us of this, okay? Our concrete example, we're just going to be rolling a single die. 6-sided die. What are all your possible outcomes? A 1, a 2, a 3, a 4, a 5, or a 6. That's everything you can roll on a 6-sided die.
Yeah.
So notice S is equal to that set of all outcomes. S is a set of all your outcomes. What is the probability of me rolling a 5 if it's a fair die? 1 in 6. What's the probability of me rolling a 2?
Also
1 in 6. So our probability function for any little s you choose in big S is just 1/6. Maps everything to just the number 1/6. Now when I say what did you roll, that's what X here is going to represent. So when your die actually shows a 1, we say you rolled the number 1. When you rolled a 2, we said you 2. 3, 3, 4, 4, 5, 5, 6, 6. So in this case, our random variable is just mapping the number to what you rolled. Good? Nice and straightforward so far? So now let's just calculate the expected value of X. In other words, what would we expect you to roll? How did we think about last time? Let's say we're playing a game where I'm going to pay you in dollars whatever number you roll. If you roll a 2, I'm going to give you $2. If you roll a 5, I'm going to give you $5. How much I charge you to play this game so that in the long run it comes out even?
Wasn't it like $2.50 or $3 something?
We should play. You'll figure it out real quick. How much I charge you to play that game?
You want to charge it so that you break even more often than not.
Well, how much I charge you so it's a fair game. So odds are in the long run I break even. You remember when we averaged down a bunch of die rolls, I had you all give me a bunch of random numbers? And what was it getting close to?
3.5.
3.5. Or the average of all your rolls. Make sense? So in this case, that's exactly what the expected value is going to give you. Intuitively, that's what it gives you. The average you can expect. So let's now calculate the expected value of x. Here's our function x over here. We're going to calculate the expected value of x. Here's its exact definition. So just looking at that definition, what does this definition say? It says pick a little s and big S. Here's our big S. So I'm going to pick a little s and big S. I'm going to start with 1. And I'm going to plug that into x, and I'm going to plug that into p and multiply them together. So plug 1 into x and p, multiply them together. And then add it to what you get when you plug 2 into it. And then add it to what you get when you plug 3 into it, and 4 into it, and 5 into it, and 6 into it. And you keep doing it until you do everything in s. That's what the expected value is. Take everything in s, plug it into x of s times p of s, and keep adding up the results. With me so far? So let's now actually calculate this. So what is x of 1? When I plug 1 into the function x, what do I get? 1. X just spits out whatever you input.
Oh, into X.
That's all x does. Get my shadow there. Right there.
Yeah.
Maps 1 to 1. So what is x of 1?
1.
Just 1. Am I losing you on this?
Kind of.
So here is our function. Where's my laser? Too slow with this. Here is our function x. What does x map 1 to? What does it pair it with? Map to pair with, same thing. So it just pairs 1 with 1. So x of 1 is just 1. X of 2, just 2. X of 3, just 3, etc. So what is x of 1 here?
1.
It's just 1. Now, we're going to multiply this by, can't write very good. We're going to multiply this by the probability of a 1. What was my probability of 1 now? Looking at my probability function. 1/6. So it's just going to be 1 times 1/6. And now we're going to add that to what's x of 2?
2.
Just 2. X is the function. It just maps everything to itself. That's all it's doing. So that's going to be 2 times, what was the probability of x? 1/6. Plus, what's x of 3? 3 times the probability of 3? 1/6. And now I think you're getting it. Plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. Everyone good with me just going? Sorry, terrible handwriting on my knee. Okay. Now, what does this actually equal? So, let's just add up all the numerators and then divide by 6 when we're done. So I have 6. What's 6 plus 5 plus 4 plus 3 plus 2 plus 1? Well, 6 plus 5 is,
11.
plus 4 is,
15.
plus 3 is, plus 2 is,
20.
plus 1 is.
21.
So this came out to 21/6. Or, another way we could have said that is 7/2.
7? Oh.
Same thing. Or, what she was thinking, 3.5. Which is what we expect it to be. Okay, that was if x was that. Let's instead look at some random variable y. This time y is going to map each s. I'm not going to write out all the order pairs this time. I'm just going to use functional notation that you're more used to. So I'm going to say that y of s, for anything you plug in there, it just spits out 2 of that thing. So if you roll a 1, I'm going to give you $2. If you roll a 2, I'm going to give you $4. If you roll a 6, I'm going to give you $12. Now how much should I charge you to play the game? If we want the game to be fair.
Why?
How much more? If I should charge you $3.50 when you get how much you roll, and now I'm going to start paying you double, how much should I charge you?
$7.
7, twice as much. Intuitively, right?
There's no way it's right though.
It's 100% right. And I was hoping that that would just appeal to your intuition, but let's go ahead and now just calculate the expected value now of y. So, what is the expected value of y? Well, that is going to be equal to y of 1. What do I get when I plug 1 into my function y over here?
2.
So when I plug 1 into y, it spits out 2. Times the probability of 1 is 1/6. Okay, plus, what do I get when I plug in 2 to y? 4. Times 1/6. Now what do I get when I plug 3 into y? 6. Times 1/6.
Might be right.
Might just be. Plus 8 times 1/6. Plus 10 times 1/6. Plus 12 times 1/6. Now if I were to add all those up, what would I get?
14 hours.
Okay, let's redo it. 12 times 1 is? Well, so we'll just add up all the numerators. 12 plus 10 is?
22.
Plus 8 is?
30.
Plus 6 is?
36.
Plus 4 is?
40.
Plus 2 is?
42.
Ah, so we got 42/6 rather than 21/6.
21. I said.
42/6,
Right. Okay.
which is also equal to 7. So rather than 3.5, we got 7. So this one up here was 3.5. The second one we got 7.
Okay.
Hopefully that's pretty intuitive. So there's calculating two different expected values on the exact same sample space with two different random variables. Good?
Hold on, let me see here.
Ah.
Fine.
Okay,
That should be it.
thank you.
Yeah. Okay. Good? All right, let's redo a couple theorems that we did last time real quickly. Little bit of dense notation. But since it's the second time proving it, hopefully now it's easier for you to follow. So the first thing we're going to prove is that the expected value of the sum of two real random variables is just equal to the sum of their expected values. Again, we already proved this last week, just going over it again. Good? Okay, so the expected value of x plus y, by definition, what was our definition for expected value coming back up here?
The sum of x.
It's the sum for every little s and big S of whatever your random variable is that you're calculating the expected value of times your probability function. So our random variable that we're doing is x plus y. Function plus a function just returns a function. So still just a function. So this is the sum of x plus y of each little s and big S. I'm not going to write the little s and big S at the bottom of the sums anymore. From here on out, it's implied. And then I'll write the sum when it's something different. So the sum for every little s and big S of x of s plus y of s all times our probability function. Just plugging into the definition. Now I'm just going to distribute p of s to both the x and the y. So just distributing over these parentheses, distributing this term. Good? So multiply it in. That's going to be x of s times p of s plus y of s times p of s.
Oh, cool.
And now I'm just going to use associativity to do associativity and commutativity to do the sum of all these terms first, and then we'll add up all these terms after. So just splitting it into two sums. So do all the x of s, p of s terms, sum them up first, and then sum up all the y of s times p of y terms. And then this is exactly the definition of the expected value of x, and this is exactly the definition of the expected value of y. So what is so useful about the theorem is it stops us from having to recalculate expected values over and over again when we know some sort of base case. In particular, if you remember our repeated and trial space, where you would build it from some base sample space, you can do a similar thing with your real random variables. So now let's look at the case where we're now rolling two dice. So rolling two 6-sided dice. What are all my possible outcomes? Well, my first die could be 1 and my second die could be 1. My first die could be 1 and my second die could be 2. My first die could be 1, my second die could be 3. All the way down to I could have rolled a 6 and 6. How many things, oh boy, how many things are in this S?
36.
36, one for each of the possible rolls. What are the odds that I roll exactly my first die of 4 and my second die of 2? 1 in 36. What are the odds that I roll a 6 and 6?
Also 1
1 in 36. Each outcome has a 1 in 36 probability. Good? Okay. So now, here's the random variable I'm going to create, x. X takes some rule where the first die shows A and the second die shows B, and it's just going to return A plus B. So x is exactly what you intuitively think when you said, what did the die roll?
Right.
If I rolled a 4 and a 2, what was my roll?
A 6.
A 6 is what you would call that. How did you get that? You took whatever the first die showed and added it to whatever the second die showed. So x is just telling us our rule. Now, if we wanted to calculate the expected value on this thing, just using our exact definition, how would we do that? We'd have to do x of 1, 1 times the probability of 1, 1 plus x of 1, 2 times the probability of 1, 2 dot 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 x of 6, 6 times the probability of 6, 6. And do all 36 of those terms. That sounds like a nightmare.
Yeah.
But we already know the expected value for rolling one die. What is it?
3.5.
3.5. We just barely calculated that right up here. Right?
You good?
And we set up our expected value here, so it's just the sum of the two die. So we can think about this as a sum of two expected values, defined the same way we had defined up here for just one die. And so if the expected value of one die was just 3.5, then the expected value of two die is
7.
7.
That makes sense.
And that's just using this exact idea. The expected value of the sum is just a sum of the expected values. So if the expected value of one die is 3.5 and the expected value of a die, or the expected value on another die is 3.5, then the expected value of the sum is just the sum of those expected values. And you don't need to rework through all 36 of those terms.
That's nice. It's quite nice.
And so we can instantly say the answer here is just 7. And notice how easy it is for you to generalize. What if I were rolling 10 dice?
35.
I have 10 dice, and I'm going to randomly roll. I add it all up. I do it again, I add it all up. I do that a trillion times, and I try and take the average. What would I expect the average to come out to?
35.
And the answer is just 35. It's just 3.5 times 10.
So it's just n times 5.
Well, it's just reusing this exact principle, but with the sum of 10 terms.
Right.
So, nice and simple, hardly even have to think about it. If you tried to plug in using 10 die into our actual definition, what a nightmare.
Would be full.
How many terms would that have?
A
A lot. That's exactly how much it would be. I'm glad you didn't round. Yeah, I don't know 6 to the 10 off the top of my head.
Yeah, that's
2 to the 10 is already 1,024. 4 to the 10 is then going to be past a million. 6 to the 10, I don't know.
You're losing me.
probably right.
It's for sure over a million. I'm trying to come up with some ballpark number to help you think about how stupid massive that would be. But I'm rounding unlike her. Okay, so now our next little theorem. Again, pretty straightforward. The expected value of some constant times x is just that constant times the expected value of x, where c is just some real number. So remember, x here is, what's x?
A random variable.
A real random variable. What is a real random variable?
It's a function of the
It's a function. So x is a function, c is just a number. So we're taking a function and we're scaling it up by c. So don't think that this is, we're not plugging a number into the function. We're plugging a function into the function. Right?
Yep.
You've done this a bunch of times. If you know that f of x is equal to 2x, then what is 4f of x equal to?
8 times.
Ax. Right? You know how to take a function and multiply it by a number.
I don't know if we've done that.
Well, you've definitely done it a bunch of times. Whether you've taken the time to explicitly talk about it as think about a function multiplied by a scalar, I don't know.
Oh, yeah.
But the point is, you've done that a bunch of times. That's what we're doing in here. So c is like that number 4. It's just a constant. Okay, let's really quick go through the proof and then talk about where we've already done an example of this. So we are doing the expected value of c times x. By definition, what is that going to be? Well, we're going to do the sum for all little s and big S of whatever our function is here, when you plug in little s times the probability of little s. Now, I can use associativity to put my parentheses right here and right here. Just move my parentheses over. And then factor the c out of my sum because it's the same for each term. And then this sum, the sum for all little s and big S of x of s times p of s, by definition is, this by definition is
The expected value.
it's just the expected value of x. So there we go. Now, what does this mean? Once again, let's go back to, we're rolling a single die. What's the expected value? 3.5. If we instead change the game, I said, if you roll a 1, I'm going to pay you $2. If you roll a 2, I'm going to pay you $4. If you roll a 3, I'm going to pay you $6. What was the expected value when we scaled it up by 2?
7.
It was 2 times higher, or 7. Similarly, if I said, whatever you roll, I'm going to multiply it by 10. So if you roll a 1, I'm going to give you $10. If you roll a 2, I'm going to pay you $20. If you roll a 6, I'm going to pay you $60. Now what is the expected value?
35.
Just 35. Just 10 times whatever it was for your single die. So that's all this is saying. So, let SP be the sample space for a single die. X of S is a function that spits out twice of whatever you rolled. If you roll a 1, you get moved 2 spaces. If you roll 2, you get moved 4 spaces, whatever. What's the expected value of X?
7.
It's just 7. It's just 2 times whatever the expected value was for just X. So 2 times 3.5, or in this case, 7. Good? Okay, and then our final theorem, which just combines the 2 previous theorems. So the expected value of some constant, A here's just some real number, times X is a function, plus B, a real number, times Y, a function, added together is going to be a function. So once again, still just plugging in a function. This is equal to A times the expected value of X plus B times the expected value of X, where A and B are real numbers. This is just using our previous 2 proofs. So the expected value of a sum of 2 functions is just equal to the expected value, or the sum of the expected values. So we already know if you have the sum inside, you can pull it outside and do the expected value on each half. That's just using the first thing we proved. And then using what we just barely proved up here, what we proved up here is you can pull constants outside the expected value. I can pull the C out. So I can take the A and pull it out, which is how I got this term, and I can take the B and pull it out, which is how I got this term. And we're done. Okay, our last theorem from last time. The expected value of X times Y is just equal to the expected value of X times the expected value of Y. Hopefully now, this is all coming back to you and we don't need to reprove that one. We're good? Just coming back to you? You don't need to see the proof of this? Well, you should, because it's not true.
Oh, that's right.
Oh, that's right. So let's go over.
Something fishy.
There was something fishy. You only get points for saying it beforehand. Scream out, there's something fishy, and you get an extra credit point. You ever say there's something fishy and you're right, I'll give you an extra credit point.
Okay.
Okay, so let's go over our example showing that this is not true. How do you prove a statement false? One single counterexample. So I'm going to come up with one sample space with one expected value, or I guess we're going to have to come up with 2 expected values, real random variables that make this function false. So here's the one we did last time. We are going to be flipping a coin twice. That's it. Flipping a coin twice. Where are my possible outcomes?
Heads and tails. Well, there's,
I'm flipping it twice.
yeah, so heads.
So I could have gotten heads, heads. I could have gotten heads, tails. I could have gotten tails, heads, and I could have gotten tails, tails. What are the odds if I flip the coin twice, I get heads and heads? 1/4. What are the odds I get heads, tails? 1/4. Tails, heads, 1/4. Tails, tails, 1/4. Each of them are 1 in 4 chance, 25% chance. Good so far? Okay, so here's our sample space for just flipping a coin twice. X sub h here is just going to spit out the number of heads in one of your flips. X sub t is just going to spit out the number of tails in one of your flips. So to write it out, in full detail, completely write it out, here's exactly what x sub h is. It's the function where if you give it h, how many heads is that?
2.
2, so it's going to spit out 2. If you give it ht, how many heads is that?
1.
1, so it's going to spit out 1. If you give it th, that only has 1 head, so it spits out 1. If you give it tt, it's going to spit out
0.
0. This function makes sense? Good? Just spitting out however many heads were in the string. Similarly, this one's just going to spit out however many tails were in there. So x sub t, if you give it h, it spits out 0. If you give it ht, it spits out 1. If you give it th, it spits out 1. If you give it tt, it spits out 2. Counting the number of tails this time. Good so far? So let's calculate the expected value on each of these. So let's start by calculating the expected value of h. Now, how do you calculate the expected value? You take every single little s in big S, you plug it into your function, whatever the function is you're calculating the expected value of, and multiply it by its probability. So I'm going to take HH and plug it into XH. So plugging in HH for our little s here, what does this term come out to when I plug in HH?
2.
That one comes out to 2. Times, what was its probability? 1/4. Okay, now add that to when we plug in our next thing in S. So this time we're going to plug in HT, and we're going to plug that in right here for these S's. So these S's are now going to be this HT. So when I plug in HT into this function, what does it spit out?
1.
1, because there was only 1 heads. Times, what was the probability of HT?
1/4.
1/4. Now I'm going to plug in TH. TH has how many heads?
1.
1. What was the probability of getting a T then an H?
1/4.
1/4. And now I plug in, finally, our last one that we haven't done yet, TT. Plugging in TT, how many heads does tails have?
0.
0. Times the probability of tails
1/4.
1/4. And it comes out to
1.
just 1. You see that? This is a half, this is a fourth, this is a fourth. A half plus a fourth is 1. Good? Yes? Okay. Now let's do the exact same thing, but calculate the expected value of x sub t. Remember, x sub t counts however many tails are in it. So I'm going to plug HH into x sub t, and what do I get? 2.
2. Oh.
You're right. 0 times what was the probability of HH? 1/4. Now add that to what I get when I plug HT into x sub t. 1 times its probability.
1/4.
Now we're plugging in TH. Now we're plugging in TT.
2.
And you add all those up, and what do you get?
1.
1.
Can you draw your 4 again? Just show me how you draw a 4.
How I draw a 4?
Why? Ugh.
Ah,
Why are you going from bottom up?
I swear, you can't write anything in this class without being judged. Okay. Now let's calculate the expected value of x sub h times x sub t.
10.
Okay? So, first thing I'm going to do is plug HH into both of these. So when I plug HH into x sub h, that spits out
2.
2 times when I plug HH into x sub t, it spits out 0. And now times the probability of HH,
Which is 1/4.
1/4.
What? Yeah. Okay.
Okay, now repeat. So now I'm going to plug HT into x sub h, and that spits out
1.
1. And when I plug it into x sub t, that spits out.
1
So 1 times 1.
is 1.
So we're adding this, yeah, but try and just write it out so that we see every little detail. Sorry if you can't read that. 1 times 1 times 1/4, right?
Yeah.
Now this time we're going to plug in TH. So when I plug in TH to x sub h, it spits out 1. X sub t spits out 1. And then once again times the probability. And now we're plugging in TT. So TT into x sub h gives us
0.
0 times, when we plug it into x sub t, we get 2 times 1/4. And now when you do the algebra on this, what do we get?
1/2.
So this is 0, this is 1/4, this is 1/4, this is 0. So a fourth plus a fourth is a 1/2. And notice that 1/2 is not the same thing as 1. If we did the product of their expected values, x of h times x of t is 1 times 1, which is 1. But the expected value of x of h times x of t is equal to 1/2. So notice that this is not the product of these two things. This equation is not in general true. It's a bad equation. We don't like it. Oh,
Okay.
good?
Minecraft is better.
Okay. Is that what we need to do? Make you come up with commands for cloning in Minecraft and stuff like that?
Can we have a small break?
Right now.
Almost.
Oh,
Okay.
We'll do a small break when we get to variance. You need a small break?
Yes.
Okay. All right, we'll go ahead and do a small break, and then we'll come back to it.
Should come back to Minecraft.
Better to give you a break if you need it.
Thank you.
All right, let's see if I can pause this. Go ahead. We were only a half hour in.
I'm wearing Sheen, so I'm probably wearing like half plastic, but
Yeah.
Uh-uh.
Uh,
Stop sharing your eyes. I started my recording.
oops. Same unit. Are you screen
It
sharing
still
to
thinks
the,
I'm sharing.
you screen sharing to the projector or to the MacBook?
To my MacBook Pro.
You can do that.
Yes. Okay. Phew, we can finish the lecture.
What are
You were terrified.
So,
All right. Let's
How much longer do you think the lecture is?
maybe another half hour.
I'm just trying to gauge.
Depends on how well you pay attention.
I'm trying. I truly am.
That is
okay?
awesome. All right. So now let's calculate our last theorem, or let's prove our last theorem. But before we prove it, let's remind ourselves of something that we proved in the past, and then maybe go over an example of it to help it appeal to your intuition. So we have this second way of calculating the expected value.
yes.
And instead of doing it for every little s and big S, we just said, let's look at all the numbers that x can spit out, and then multiply it by the probability that x spits out that number. So to give you a concrete example, the way that we actually calculate the expected value of rolling 2 die, so put that theorem on hold for a second. Let's calculate the expected value now of x, where x is your rule for rolling 2 dice. So if you roll a 1 and a 1,
Zero.
you get a 2. And the probability of you doing that is
1 in 36.
1 in 36. So, let's see how we actually did that. Go back to white here. So, down here, ignore the theorem for a second. X here is 2 die. So we said you spit out a 2, and you spit out a 2 how often?
1 in 36 times.
1 in 36. 1 in 36 of your rolls, the real random variable that we're using, x, is 2.
Right.
Plus, what about a 3?
Also the same.
How many ways can you get a 3? You do that with a 1 and a 2 and a 2 and a 1. So it's 2 in 36 is the probability of that one. Right?
Yep, sorry.
And for a 4, how many ways can you get a 4? 1 and a 3, 2 and a 2, 3 and a 1.
4 ways.
3,
So 3 in 36. And how many ways can you get a 5? 4 in 36. And this will make sense if you remember that square I showed you for how to quickly calculate these values. And how many ways can you get a 6? 5 in 36. How many ways can you get a 7?
6 out of 36.
6 in 36. Oops. Plus. 6 in 36. How many ways can you get an 8? 5 in 36. How many ways can you get a 9? 4 in 36. How many ways can you get a 10?
3
3
in 36.
in 36. How many ways can you get 11?
3 in 36.
Plus 11. times 2 and 36, and just not enough space. How many ways can you get 12? 1 and 36. And so let's add up all the numerators. I don't know which way is easiest. Probably starting in the back. So 12 times 1 is 12. Okay, 2 times 11 is 22. So 12 plus 22 is
34.
34. Plus 30 is
64.
plus 36.
100.
100. Plus 40.
140.
140. Plus 42.
182.
Plus 30.
100 or
212.
12.
Plus 20.
232.
232. Plus 12.
244.
244. Plus 6.
250.
Plus 2.
252.
252. So that came out to, that came out to 252 divided by 36. And if we did that correctly, 252 divided by 36 is 7. Okay, we did it all correct. So that came out to 7. So that's the way we calculated the expected value last time.
Right.
And this way of calculating the expected value, notice that we did not do it for all 36 terms. We just said, what could the output of our real random variable be, and multiply it by the probability of that output. So our random variable that we were using, the sum of the two die, could have been a 2, a 3, a 4, a 5, a 6, all the way up to a 12. And then we just multiply by the probability that x gave us that output. So that was this way of calculating an expected value. Okay, so now what are we going to prove? We're going to prove that if you have two real random variables, x and y, and they are independent, then the expected value of x times y is equal to the expected value of x times the expected value of y. Now, what did it mean for x and y to be independent?
Their probabilities don't depend on
The probability of getting both of them is the exact same as a product of their probabilities.
Yeah.
It's like flipping a coin. Say x was that our first flip is a heads, then we spit out 1, 0 if it's not. Y is our second flip is a heads. My first flip being a heads has nothing to do with my second flip being a heads. Those are completely independent. And if we were to calculate that probability, it would just be the product of their two probabilities.
Yep.
Okay, so that's what it means to be independent. So now let's go ahead and prove that this equation holds when x and y are independent real random variables. So what is the expected value of x times y using this definition? We're just doing the sum over all real numbers a times the probability that x times y is in fact equal to a. Remember, our expected value that we're calculating is x times y.
And how did we get that formula again?
This formula?
Yeah.
We just proved it. This was basically a way of regrouping what exactly this definition gives you. It's just grouping by all the terms where the x gives the same output. So you notice when we did it down here, that's the way we were grouping. So I grouped all my rules that are a 6 together.
Okay.
And all my rules that were a 7 together. So it was just a regrouping on this as the intuition for how you prove it. But we went through all the detail to make sure you could actually see it in the math.
Right.
And you might remember I went through the pains of writing out by hand,
Yeah.
rolling 2 4-sided die so you could actually see how we were regrouping terms.
I remember that.
So if that's not appealing to your intuition, probably worth going back and looking at that previous video and seeing how we actually manipulate those terms. But anyways, so by definition, the expected value, not by definition, but using this theorem, the expected value of our function is just equal to a times the probability that our function spits out a. So our function is just x times y instead of just x.
Yeah.
You see how we're just plugging into this definition? Okay. Now, if x times y is equal to a, what does that mean? That means x spit out a number and y spit out a number such that their product was a. So x had to spit out some number and y had to spit out some number because they're real random variables. And whatever those numbers were that they spit out had to multiply together to be a. So all we're going to do now is we're going to resum, maybe zoom in on what this sum is saying. We're going to take all b, c, and the real numbers, such that b and c multiply together to be a.
Okay.
And so the probability that x times y is equal to a is the same thing now as the probability that x was b and y was c, where b and c were two real numbers that multiply together to be a. That's how we go from here to here. That b and that c are just two real numbers such that their product gives you a.
Okay.
So good with going from this line to this line? Okay. Now, if a is just b times c, going from here to here, we're just going to rewrite the a as b times c. That's one step we did. Also, we use the fact now that x and y are independent. So the probability of x being b and y being c is the exact same thing as
The product of the probabilities.
the product of the probabilities. So the probability of getting both is the same thing as the product of the probabilities.
Right.
Good?
Yep.
What's the odds of me flipping heads on my first coin flip?
1 half.
What's the odds of me flipping heads on my first coin flip and then flipping heads on my second coin flip?
1/4.
1/4. You did a half times a half. Those were independent events. Same type of thinking. The probability of my first one being heads and my second one being heads is just a product of the probabilities. Okay. So that was using our definition that we needed in order to make this statement true. So that's using that definition and just replacing the a with the b and c. Now, right now, notice that these terms are currently grouped by when this is the same a.
Okay.
Now I'm going to regroup it. So at first, we just pick our b here that we want. And then afterwards, find the c such that their product would have given you the a. So all the ones now that have the same b term is what we're grouping by right here. So this, going from here to here, is using commutativity.
Okay.
This we were doing where their product is the same number, doing all those terms first. Now we're doing where whatever this first number is in the product is what we're going to group by first.
Okay.
So going from here to here, just a regrouping of terms by our b's. Okay. And now, notice that we're saying, if you're used to, I don't know, programming, you think about this as a loop within a loop.
Yeah.
This is the outer loop, this is the inner loop. But say it not programming terms. For every b, we then do, for every c, do this. So notice inside this inner sum, b is a constant. So we pick a b out here. So we're looping over all our b's out here. And then inside this inner sum, b is now chosen to be a particular number.
Right.
And we now find the c's such that this is true. So inside this inner sum, b is a constant, and the probability that x is equal to b is a constant. So we can pull those out of the inner sum. So going from here to here is just factoring out the b and the probability that x is equal to b
So
from the inner sum.
does that sum say, are you iterating over the b's for that too?
Yeah, so this is saying, pick a b out of the real numbers.
Mm-hmm.
You can now calculate this. And now, for every c in the real numbers, we got to calculate this.
With that same b.
With that same b.
Okay.
Taking their product, and we're adding up the results now for every b that we choose here.
Correct.
So pick your b, then do it for all the c's corresponding to that b. Now pick your next b, do it for all the c's corresponding to that next b. Again and again and again. Okay, now notice in here, this sum now is going for every c in the real numbers, calculating this every single time. It doesn't matter what your b is. So if this evaluates, for our first b, if this evaluates to some number, like 27 for this inner sum, whatever it is, if that comes out to 27 when b was 1, what's going to come out to when b is 2?
With the same c?
This is summing for all the c's.
Oh.
So this sums for every c times the probability that y was c.
Oh, and it comes out to 27.
And let's say that that just came out to some number 27.
Uh-huh.
So if it came out to 27 when b was 1, what would it come out to when b was 2?
It would be 2 times the probability of b times 27.
No, not when you multiply it, just this inner sum,
Oh,
inside the parentheses. If this came out to 27 when b was 1, what would it come out to when b was 2?
it's just
27. What would it come out to when b was 3? 27.
Yeah.
Notice that this is no way dependent upon b. So whatever number this is, it's just a number for all those b's.
Yeah.
So you can think about this almost as a constant now, and you can factor that out of this sum.
Okay.
So now I'm factoring this thing out of this sum, and that's what we did here. And that's probably the hardest step to follow. Going from here to here is realizing that this sum is the same for every b's and factoring it out. You see that?
Yeah.
And there we go. This, by definition, is the expected value of b. Not by definition, but using this same thinking up here. So this is the expected value of x, not b, and this is the expected value of y.
Yeah.
So there we go. There's the proof of that. Okay. One more easy example. I know that was a lot of theorem to follow. Back to easy mode. Just a simple example. Simple example where we will not be using that theorem. Okay. Our simple example now is one more way we can use expected value, and we can use it to find the center of mass for a bunch of objects. So here's the game we're going to play. I got these objects. I'm calling them the objects 1 through 10. That's the name of my rocks.
Okay.
I'm very creative with my rock names. Over here is how much each of my rocks weigh. So I have a rock. Oh, sorry, no. All my rocks weigh 1/10 of a pound. Over here is where I'm going to place my rocks on some teeter-totter. Here's my amazing drawing of our teeter-totter, where I'm going to place my rocks. So rock 1, it weighs 1/10 a pound. I'm going to put it at position 1 on my teeter-totter. Rock 2, I'm going to put at position 1. Rock 3, position 1. All the way down to rock 10, I'm going to put at position 8.
Okay.
Let's just start doing this so you can see it. So rock 1 goes at position 1, so here's rock 1 at position 1. There it is. Rock 2 also goes at position 1. So I stack it right on top of it perfectly balanced. These things can't tip over.
Okay.
It's glued on there. Rock 3, where does that go?
One.
Also at position 1. Rock 4, where does that go?
One.
Position 1. Rock 5, where does that go?
Position 2.
Position 2. Rock 6, where does that go?
Same.
Position 2. Rock 7, where does that go? 8. And same with the next rock, and there's 4 of them at 8, right? Sorry, bad drawing, but hopefully you can understand it. The question now is, where should I place this so that they're perfectly balanced? We'll assume that the board that they're on is weightless. So where should I put this so that it perfectly balances these rocks?
Just your weight.
And so I want to find the center of mass of this system, or in other words, the expected value, which also gives you the center of mass. So let's calculate the expected value really quick of this system. So what is the expected value? Remember, we need to take every little s and big S, plug it into x, and multiply it by its probability. So what is x of 1? When I plug 1 into x, what do I get? So, oh, didn't mean to do that. That was on my laser. Over here it tells me what x spits out for 1. If I plug in 1 to x, it spits out 1. So x of 1 is 1 times the probability. What's the probability of 1? 1/10. And for our analogy, probability here is acting the same way that weight would in physics. So we're assuming that they all have the same weight, or they're weighted equally. Okay, when I plug in 2 to x, what do I get?
Also 1.
When I plug in 2 to x, so here's my function telling me what x spits out for each input. So when s is 2, when I plug in 2, x spits out 1. Or in other words, rock 2 is at position 1. So x of 2 is 1 times its probability is 1/10. All right, what's x of 3? 1 times 1/10. What's x of 4?
1.
Times 1/10. What's x of 5?
2.
Times 1/10. What's x of 6?
2.
Times 1/10. And then all the last ones spit out 8. X of 7, X of 8, X of 9, and x of 10. And now when we add that all up, what do we get? So let's just add up the numerators and then we'll divide by 10 when we're done. So 8 plus 8 is,
16,
plus 8 is,
24,
plus 8 is,
32,
plus 2,
34, 40,
divided by 10,
4.
4. And so if we wanted to perfectly balance this pendulum thing, then we should take this thing right here and we should move it over to 4. And that would perfectly balance the system, assuming a weightless board. So one last use case for expected value, finding a center of mass.
That's cool.
For all of you in physics, since you're all in that class. Okay, so now our last concept is variance.
Is that what they meant by like a weighted average?
Yes, it's also similar to a weighted average, same concept. Weighted, though, would be different probabilities.
So you're weighted.
Okay, the last concept that we have to talk about is variance. Intuitively, that was a nice sigh. Intuitively, what's variance? It's how spread out our data is. So let's say I've got these 3 random variables, x, y, and z. X, whatever it is, I don't care what sample space we're on, it's just going to spit out a 2 half the time, and it spits out a negative 2 half the time. Trying to pictorially represent it over here on the right side, whatever x is, if we were to do like 1,000 cases, a bunch of them would come over here at negative 2, and a bunch of them would come out over here at 2. And so here's pictorially looking at our data.
Okay.
For y spits out 10, 0.1% of the time, spits out 0, 99.8% of the time, and spits out negative 10.1% of the time.
Okay.
So if I were to run through 1,000 times on y, we would expect to spit out negative 10 once, spits out 1 once, and then spits out 0 998 times. So here's the data on y. Finally, for z spits out 5 1/3 of the time, 0 1/3 of the time, negative 5 1/3 of the time.
Is that height? Does the height of the graph?
The height has nothing to do with anything. I'm just doing it at 3 different heights
Okay.
so that you can all see them on the same graph.
Okay.
So we're just looking at how spread out from their center they are, is all we care about. So z here spits out negative 5 1/3 of the time, 0 1/3 of the time, and then 5 1/3 of the time. Make sense?
Don't they all have an expected value of 0?
Yeah, so notice that they all have an expected value of just 0. Right? Calculating the expected value of this, it would be 2 times a half plus negative 2 times a half. 0. This one would be 10 times point 0.001.
Oh, right.
0 times 99.8. And negative 10 times 0.001.
So it's cancel out.
And so they would all cancel out to 0. And then finally, z here, they all cancel out to 0 as well.
Right.
So yes, notice that they all have an expected value of 0. We kind of think about the expected value as their center. So they're all centered at 0 is another way you can think about that. Make sense so far? Now just intuitively, what data is the most spread out? Which data is the least spread out?
Green's most spread out. Or-
So intuitively, which one's the most spread out?
Because it goes
Or
from
blue.
Blue reaches the furthest, but would you call that data the most spread out?
I don't know. Probably not.
Probably not. These are like weird outliers, and almost all the time, all the data is right there at your center. Green, you would probably say, is the most spread out. Blue, the least spread out, where red is somewhere in between. So here you and I are. We are going to try and come up with some equation that we want to mean how spread out our data is. We're just going to make one up, you and I.
Alright.
So here's our data. Whatever our equation is, we want to say, blue, that one's the least spread out. Green, yeah, that's the most spread out. And red is somewhere in between.
Okay.
And so how might we come up with how spread out our data is?
A mix of probability and position is off.
Yeah, we could probably say for each point, let's just calculate how far away it is from the center. And do that for all our points.
Does the center mean expected value?
And the center is the expected value. So I set the case where it's 0 just to help it be very clear. And so here's a very natural way that you might think about our variance. Our variance, how spread out our data is. We'll look at where our data point is. X of s is going to be where our data point is. So for x, that would be 2 and negative 2 is where those kept coming out. For y, 10, 0, and negative 10 is where our data points came out, here, here, and here. And for z, they came out here, here, and here. So x of s is just where your data point comes out. And then remember, I know I mentioned this at the end of lecture, kind of after the fact, but mu, that Greek u, mu is how it's pronounced with an m. It's just shorthand for the expected value, and it's just understood from context
That's right.
which random variable you're talking about the expected value of. So just shorthand for writing the expected value so I don't have to keep writing this over and over again. So let's see how we set up our variance equation here. We say let's take the number our data point spit out, in other words where it's located, subtract it from whatever our expected value is, so that's how far away it is from the center, and then multiply it by the probability that it was there. Add all those up and we'll say that that's the variance. That's how far away the data is.
So x of s is how far away it is from the center.
X of s is its where it is.
Where it is. Okay.
Mu is the center.
Okay.
X of s minus mu now is its distance from the center.
Oh, you take the absolute value of that.
Don't you need to take the absolute value of that? Yes, you'd have to take the absolute value. What's going to happen if we don't take the absolute value?
You get negative distance.
Well, let's see what happens when we don't take the absolute value. Let's see how we get in trouble with this thinking. Okay? So if this were our equation for variance, let's see what would happen. So variance, we're saying, let's use this sum. Now it's understood if I don't write anything down here, it's for all little s and big S. So the variance, distribute the p of s into each of these.
Okay.
That's how we got to here. Good? Now I can do all these sums first and then do all these sums next. So that's going from here to here. Just split it up into two sums.
Good.
So just split it up into two sums. What is the sum of x of s times p of s for all little s and big S by definition?
It's the expected value.
That's the expected value. Notice over here, mu is just a constant. Negative mu is a constant, so I can just pull that out. So going from here to here, this is the expected value. Pull the negative mu out of the sum.
Yep.
What is the sum of all our probabilities?
1.
1. So this just comes out to 1, and so we get expected value minus mu. What's expected value minus mu?
The expected value is
0. Because mu is our expected value. That's what mu means. So this is the expected value minus the expected value. It comes out to 0. Why did it come out to 0? Well, because every time I have a positive distance over here, I have a negative distance over here. And they're perfectly canceling each other out every time. This came out to positive 10, this came out to negative 10. And so this keeps coming out to 0.
So you need to take the absolute value.
So you'd have to take the absolute value if we want to use this thinking. What's the definition of the absolute value?
It's a piecewise function.
It's a piecewise function, right? What's the absolute value of x?
X.
Well, if x is positive, then it's just x. If x is negative, then it's negative x.
Right.
And so we hate working with expected values. Or sorry, we hate working with absolute values in functions if we can get away from it. But our problem is that we're getting negative numbers here. And so here's the actual definition for variance now.
You want to take the negative of it?
It's the expected value of x minus mu, exactly what we had here. But now let's square it, so it's always positive.
So you'll get a number that's, won't you get a number that's way bigger than what you actually think?
Well, we're coming up with a definition here.
Right.
And our intuition is, well, in some sense, we want to capture how spread out the data is.
Why don't we take the square root of it? Yeah, actually, I don't know.
Because once you take the square root, you have to handle the plus or minus case. So we don't want to deal with a piecewise function. That's one reason to avoid the absolute values and to square it instead.
Yeah.
Another reason that we kind of like the squaring is what happens when you square really small numbers?
They get smaller.
They get smaller, right? What's 1/2 squared?
1/4.
1/4. So for numbers that are already really close, it kind of means they don't really matter even more than they didn't matter before. And for numbers that are really far, now they matter much more than they did before. So it's going to make scattered data more exaggerated, and it's going to make concentrated data less exaggerated.
We want that.
And so it's another thing that we like in using this definition.
Interesting.
You could come up with a definition using absolute value. That would also give you some sense of how spread out the data is. Nothing wrong with using that. Here's one that everyone uses. And so when you eventually go to here, you've probably heard about standard deviations before. That's in some sense talking about the variance, and here's the definition ultimately backing what that means. So here's the exact definition of variance. Exactly what you might have guessed before, but we square it. Good? So now let's go ahead and calculate the variance of each of these things. And see if it works the way we wanted, where this one is the least spread out, this one is the most spread out, and this one is somewhere in between. So let's calculate and see what happens. And also just get you comfortable actually calculating the variance. So what is the variance of x? How do we calculate that?
Wait, this is the expected value of x minus mu?
The expected value of x minus mu squared.
But x minus.
It's the same thing as this sum. Notice this sum and this sum, but a square there. What is the expected value of x minus mu squared?
Okay,
You see how they're the same?
yes.
Okay, now let's plug it in for x. So back up here, x split out 2 half the time and negative 2 half the time, right? So what's its expected value? Well, this comes out to 2 half the time.
Yep.
Let me start writing. So we're going to get a 2 minus, what was our mu? 0. Our expected value for x up here was 0. Expected value of x was just 0. So, mu is just 0 in this case. And now, times, what was the probability that we got to?
1/2.
1/2. And now, plus
The negative 2.
negative 2 minus mu is still just 0 squared. Sorry, I forgot my squared. Times 1/2. Yeah, if we didn't have the squared there, it'd come out 0. And this is equal to 2 minus 0 is 2 squared is
4.
times a half is
2.
2. So the first term came out to 2, and the second term comes out to negative 2 minus 0 is negative 2 squared is 4 times a half, 2 again. And so its variance, or its spread outness, is 4. So x has a spread outness of 4.
Is there a unit for that?
Yeah, spread outness. Now you don't have units, but it's just math.
Fair enough, I guess.
Okay. Now what is your variance of y? Well, let's see. Y could spit out 10, right?
Yeah, 10 minus 0.
So 10 minus 0 squared times, how often did it spit out 10? 1 in 1,000,
Yes.
right? 0.01% is what we had written up there.
Yeah.
1 in 1,000. Okay. Plus, let's see, we spit out a 0 minus 0 squared, and we spit out a 0 998 out of 1,000 times.
No, that's right.
And then plus, our last one was negative 10 minus 0 squared, and we did that one 1 in 1,000 times. Okay, and what does this equal? Well, 10 minus 0 is 10, squared is
100.
divided by 1,000 is
0.1.
0.1. So this comes out to 0.1, this middle term comes out to 0, and then this right-hand term comes out to 0.1, for a total of
0.2.
0.2. So this one has a spread outness of 0.2,
Okay.
right?
That makes sense.
Yeah, it makes perfect sense. This one is obviously 20 times as spread out as this one. I know what you mean. You follow the math. Okay, finally, let's calculate the spread outness of z here. Does 5 1/3 of the time, 0 1/3 of the time, negative 5 1/3 of the time.
Okay.
All right, this time we'll be a bit quicker about it. So plugging in 5 minus 0 is
What?
5 squared is,
25.
so it's going to be 25 1/3 of the time. Plus, we won't bother with the 0 term. 0 minus 0 squared is 0 times 1/3 is 0. Okay, the next term. Negative 5 minus 0 is negative 5 squared, 25 times 1/3. Okay, so once again, 25 times 1/3, or in other words, it comes out to 50 thirds.
What is that evaluate to?
Or as a decimal, since you guys want it as a decimal, well, that's going to be, I guess you could say 16 2/3 or 16.6 repeating.
Pretty high range.
Yeah, so almost 4 times the spread out as x,
Almost 80 times the spread.
and almost 80 times the spread out, a bit more than 80 times the spread out as x. So this one is 80 times the spread out as blue, and this one is 4 times the spread out as red, roughly.
That makes sense.
It kind of feels okay when you look at it.
Yeah.
Okay, so there we go. There's the variance.
Cool.
So let's just do some examples. What?
There's more?
This is our last page.
Oh, it is?
And then that page.
Fun.
You take like 20 minutes a page, bro.
Not last page, it was the last page.
The last page has always been the last page. Okay,
This is the last page of
now it's just simple examples. Okay, so let's do it for rolling a single die. Let's calculate the variance. So SP for rolling a single die, X just spits out the number you rolled. How would we calculate the variance? The variance is you do 1 minus the expected value squared times a 6 plus 2 minus the expected value squared times a 6 plus 3 minus the expected value squared times a 6, etc., all the way up to 6. That's a nightmare. I don't want to calculate that.
Yeah, that's pretty bad.
Actually, that one's not too bad because it only has 6 terms, but what if we did 2 die?
36 terms. Or,
Now 36 terms, or even if you want to think about it in terms of the other way, still, difference is squared. We don't really like having to work with that.
is there
The other one was nice because it was 0 every time, right?
Yeah, yeah.
So over here, the reason it wasn't so bad to calculate is we kept having zeros for our expected values. When you don't have zeros for your expected values, it can be kind of annoying calculating the variance, even in simple cases.
Right.
So rather than calculating the variance that way, we're going to prove one more equation that's going to make calculating our variance way easier. So I'm going to prove that the variance on x is just equal to the expected value of x squared minus the expected value of x squared.
Those are not the same.
Those are not the same thing. One's squaring the function that you're plugging into your expected value. One's calculating, this one over here is mu squared. This one is not mu squared. So very different things.
Okay.
Okay, so let's calculate it. Or let's prove it, I mean. By definition, what is the variance of x?
What's your sum?
It's your sum for all little s and big S of x of s minus mu squared times probability of s.
Yep.
Now I'm going to square out this term. What's x of s times x of s?
X of S.
X of s squared. We're going to have an x of s times a negative mu and a negative mu times an x of s for a total of negative 2 mu x of s.
Yep.
Sorry, my handwriting got sloppier the further I went. And then negative mu times negative mu is positive mu squared. So expanding this out gives us this. And we still need to multiply by our p of s. Good? Distribute our p of s into each of those 3 terms and split it up into 3 separate sums. So p of s to this term, here it is. P of s to this term, here it is. P of s to this term, here it is. Good? Just distributed it to each term in the sum and then broke it up into 3 separate sums.
They all simplify.
Okay, so now the sum of x of s squared times p of s, well, that's exactly what we mean by the expected value of x squared.
Yeah.
This one, you can pull out the negative 2 mu, that's a constant. So pull out the negative 2 mu right there. And what are you left with on the inside? X of s times p of s,
Or E of X.
which is the same thing as our expected value.
Yeah.
This one, pull the mu squared out. And then you're just summing up the probabilities, which sum up to 1.
Yep.
So what are you left with? The expected value of x squared, that's still here. Remember, x of x, or the expected value of x is the same thing as mu. So this is negative 2 mu squared plus mu squared. Or in other words, negative mu squared.
Wait, it's negative 2 mu's.
Maybe I did this in just one too many steps.
No, that makes sense.
We'll write one more right here. This is the expected value of x squared minus 2 times the expected value of x squared plus the expected value of x squared. Because mu and the expected value of x are one and the same thing.
So you get 2, you get 1.
So replace the mu with an expected value of x. So expected value of x times expected value of x is expected value of x squared. Mu squared, expected value of x squared. Same thing.
Yeah.
So I have negative 2 of these, and I have positive 1 of these, for a total of negative 1 of these.
Yep.
All right, there it is.
Huh.
So, if we want to calculate the variance for a single die, what we really need now is just this expected value of x squared. we already know the expected value of x for rolling a single die. What we don't know is the expected value of x squared.
How do you calculate that?
You just calculate by hand. It's much easier to calculate an expected value directly than it is to calculate a variance directly.
Right.
And so notice, pick your poison. Do you want to calculate variance directly, or do you want to calculate this directly? Because you're already going to know this most of the time. Because you have to know this in both cases. I have to know it here. So this one you have to get either way. The question is, would you rather calculate this by hand or this by hand? And the answer is, it's almost easier, always easier to calculate this by hand.
Right.
So now let's calculate that by hand for a single die. The expected value of x squared. So we just do the rule squared, and then times 1/6, or divide by 6, same thing. So let's calculate that. What's 6 squared?
36.
36 plus 25 is? 36 plus 25. Don't give up on me now. 36 plus 25.
61.
61. Thank you. Plus 16?
75. No, 7.
77.
77. Someone here to keep you honest. Plus 9.
86.
86.
Plus 4.
90.
Plus 1.
91.
Okay, so it comes out to 91 over 6. So, now calculating the variance. How do you calculate the variance? The expected value of x squared minus the expected value of x squared.
You can literally hate me.
So, the expected value of x squared we calculated is 91/6.
Uh-huh.
We know the expected value of x for rolling a single die is 7/2.
Whoa.
So, square it is
49 quarters.
49/4. And so now this difference is your variance. Whatever this equals. And you can just plug that into your calculator. You don't have to calculate these by hand. So once you figure out the expected value of x squared, you can now easily calculate the variance. And so you don't have to calculate by hand. No one calculates the variance by hand. No one does this way.
Nice.
Everyone does this way.
What if I didn't? What if it was just different? And chose to do it
You would not want
You can choose to do it this way, and if you choose to do it this way, it will probably ingrain in you a deeper understanding of variance. If you choose to do it this way, you'll probably remember how to do it. Well, if you were taking this as a college course now down the road, you would remember in a few years still how to calculate it. Because this is really easy to remember. And so everyone remembers how to calculate variance. It's the expected value of x squared minus the expected value of x squared.
Sweet.
And so that's one that's easy to remember. So another good litmus test for someone, they're pretending they understand something. Just ask them to do something like calculate the variance on a single die roll. It's a little bit of work, but if they don't know how to do it, they're probably not an expert in probabilities. Because while it's a little bit of work, when you understand what it is, it's really not that much work. It's just figuring out how to do this.
Wait, so what's the actual variance here when we calculate it?
91/6 minus 49/4. You gonna make me reach all the way for my calculator here? Oh. Yeah, probably could have just asked Siri. When you ask fractions, though, sometimes screws up.
Yeah.
And so it comes out to 2.92-ish.
So your data is 2.92 square bar.
Yep, so your data is exactly
Exactly.
2.92-ish spread apart.
Cool.
If we make it, give exact really quick, and then recalculate that, so we'll just give it to me as a fraction. Comes out to 35/12. So there's the exact answer. 35/12 spread out. So barely just shy of 3. Okay, so there you go, there's variance. Now let's calculate the variance on rolling 2 dice.
Okay.
Once again, if we were to try and use this definition directly, that would be a nightmare. So, how do we do it? Well, for 2 dice, we just need to calculate the expected value of x squared. So, just writing it out, 2 is one of our outcomes, square it, times how often that happens. 3 is one of our outcomes, square it, times how often that happens. 4 squared, times how often we get 4. 5 squared, times how often we get 5. 12 squared, times how often we get 12. A little bit of work, but not too bad.
This
And
is-
now you can just add up 12 squared, or 144 plus 11 squared times 2 plus 10 squared times 3. Add it all up, divide it by 36, and it will come out to 329 over 6.
And this is using your other expected value, where you group the.
Well, I'm just calculating the expected value of x squared.
Right.
And now when you calculate the variance, because notice I know already what's the expected value on rolling 2 dice?
That's 7.
7. So the expected value squared is 49.
Right.
So all I really need to do is think about how to come up with this piece. So this piece, it's a little bit of work, but that isn't that hard. You don't even have to really think about it. You could have just been plugging in the calculator as you go.
Right.
I could have just plugged in 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. Or sorry, 2 squared times 1 plus 3 squared times 2 plus 4 squared times 3 plus 5 squared times 4 plus 6 squared times 5. Just do the numerators, plug it in on your calculator as you go, and then divide by 36 when you're done.
Yeah.
So this is easier to just plug into the calculator than it is to even write all the way out. And it's really easy to think about that. Remembering how to plug it when you're using this definition to the calculator can get a bit more messy. So really not that hard to calculate the variance. The expected value of x squared minus the expected value of x squared.
Okay.
That's it.
Sweet.
That's it. That's the whole chapter. That's the end of the section. You're all set for your homework. The test next week is just going to be a bunch of variance problems. That's all you're going to do. Just calculate the variance over and over again.
I don't know if that makes me feel
Promise?
better.
No, I would never promise that. But if I lie to your face, I'd probably lie about the promise too. So don't trust me, but yes, that's what's going to happen. So make sure you calculate the variance. But I'd also make sure I understand everything else in the chapter.
What if we don't have a test?
Hear me out.
Okay.
All right, so that's the end of lecture. Where you can hear out your.
You were laughing,
Ideas
but
instead
I'm
of
serious.
tests.
Short.
You're always serious when it means less work for you.